If you have a diagonal matrix or any type of triangular matrix, whether it be upper or lower, calculating the determinant is super easy. What you do is you just take the product down the diagonal. A11 times A22 times A33, and so on. That's all you need to do. This formula can be checked by using cofactor expansion, and I highly recommend that you just memorize it because it can save you a lot of time. The next thing that I want to mention in this quick overview of our shortcuts for determinant are the determinants of inverses. So the short of it is, if the determinant of A is D, the determinant of A is 1 over D, provided that that determinant is non-zero. But here's the thought process behind that. You know that if you have a matrix and its inverse, when you multiply them together, you get the identity. And the determinant of the identity matrix is 1. So the determinant of A times the determinant of A inverse by the product rule is the determinant of A times A inverse. But that's just the determinant of the identity, which is 1. So what that means is that the number, determinant A, and the number, determinant A inverse, are multiplicative inverses of each other. You can solve this formula for the determinant of A inverse. It's 1 over the determinant of A. And that's all there is to it. So let's check this with a quick little example. So for our example here, let's take A to be something easy like 1, 0, 0, 0, 3, 0, 0, minus 2, 1. This is a lower triangular matrix, so you can easily see that the determinant is 3. You get that by just taking the product down the diagonal. 1 times 3 times 1. The inverse of this matrix is also something that we can calculate easily. We don't need to use the entire Gaussian elimination formula. This matrix that I've given you is actually the product of two elementary matrices. A is the product of 1, 3, 1 down the diagonal. So this elementary matrix, and another elementary matrix that has a minus 2 off the diagonal. The row operations that correspond to these elementary matrices, by the way, are scalar multiplying the second row by 3, and then replacing the third row with minus 2 row 2 plus row 3. Let's call A the product of the elementary matrices E1 and E2. Well, then it turns out that A inverse is also a product of elementary matrices. We take E1 and E2, and when we take their inverse, notice that this becomes E2 inverse times E1 inverse. So that's what we see here, E2 inverse and E1 inverse. And those inverses are quite easy to calculate because they are elementary matrices. In the case of 1, 3, 1, E1, you turn the entry on the diagonal into 1 over 3. And in the case of the elementary matrix E2, which encoded the row operation 2R2 plus R3, we change the sign of the entry off the diagonal. And then multiplying those two together, we see A inverse, which is this matrix here. This has determinant 1/3, which confirms something that we already know, which is that the determinant should be 1 over 3 because the determinant of A was 3. So this is demonstrating both the determinant of inverses and also a method for calculating an inverse matrix. If you know that your matrix A is the product of elementary matrices like this is a quick method for calculating that inverse without having to go through the entire Gaussian elimination procedure. But just remember, you can't always just change the signs. It doesn't usually work out that way. Before we talk more about determinants, and in particular the determinant of a transpose, I'd like to just mention in passing some facts about inverse matrices, since we've been talking about them. When you have an invertible matrix, the inverse exists. That also means that the equation AX equals B has a unique solution for every vector B. And in fact, you could solve for X by writing A inverse times AX equals A inverse B, and that gives you X. The homogeneous equation AX equals 0 has only the trivial solution. It's also the case that if you take your matrix A and use Gaussian elimination to put it into reduced row echelon form, you're going to get the identity matrix. So it's row equivalent to an identity matrix. And just like we saw in the previous example, your matrix A can actually be written as a product of elementary matrices. Now, it may not be clear what exactly that product is, but it is possible to factor A as a product of elementary matrices. And if you happen to know that factorization, it's very quick to compute A inverse. And finally, the determinant of an invertible matrix is always non-zero.